Hi, welcome back. I hope you've had a chance to work through Notebook 2, and I hope that was interesting for you. Again, here are some of the topics that are covered, and I'll debrief now on some of these. The notebook introduces the idea of a distribution, which is a set of quantities and the corresponding number of times each quantity occurs, like a count or a frequency, or sometimes a probability, the fraction of responses in each quantity. In the previous notebook, we used values to compute the quantities and the number of times that each one appeared. And here was the example that we looked at. These are the responses to the political alignment question. And the quantities here are the numbers 0 through 9, and the frequencies are the number of times each one occurs. So this is a distribution, and that's one way to represent distributions. You can call value counts, and the result is a pandas series that you can use to represent a distribution. An alternative is a library called empirical dist, which I wrote, which provides a function, or rather an object, called PMF that represents a probability mass function. Here's how you use it. You import it from empirical dist, and then the function from seq, from sequence, takes any list, array, or in this case, a pandas series. It counts how many times each value occurs and puts the results into a PMF object, which is also a pandas series, but it provides specialized functions that pertain to PMFs. One of them is the bar function, which makes a bar plot showing each of the quantities, 1 through 7, on the x-axis, and a bar showing how many times each one occurs, or in this case, the fraction of the population that gave each response. So we can see that response number 4, which is moderate, is by far the most common response, and the extremes are the least. 1 is extremely liberal, and 7 is extremely conservative. We can also make a plot that shows the two bars side by side for the beginning of the survey, 1974, and the end, which is 2018. So in this figure, the blue lines represent 1974 and the orange represent 2018. And we can see what changes have happened over time. It's a little hard to tell how much of this is just random variation and how much of it is real shifts, but it looks like the extremes have increased a bit. 1 and 7 are more common, the orange bar is bigger, and it looks like maybe there's been a shift toward the right, which is literally toward the right, more conservative. One of the functions in the notebook is decorate, which is a wrapper for matplotlib functions that will set things like the title and the X label and the Y label. And you have a choice. If you like decorate, you can call one function and then pass keyword arguments to specify things like the labels and the titles. Or if you use the matplotlib functions directly, then you just call them as separate functions. In the notebook, I compute the mean and standard deviation of the political views series from 1974 and 2018. Now remember that the scale goes from 1 liberal to 7 conservative, so higher values mean more people gave conservative responses. And in this case, the mean increased from about 3.9 to about 4.0, although it's actually a smaller gap than that sounds like. It's hard to say how meaningful that shift is. It's quite small. The standard deviation has also increased from about 1.33 to 1.43, and that measures how spread out the distribution is. So if people shift from the middle toward the extremes, that would increase the standard deviation. And it looks like that has happened, although maybe by a small amount. Now, one thing to think about, the types of data that we're working with. In general, there are two types of data, numerical and categorical. Numerical values are things like integers and floating point numbers. And categorical quantities are things like, animal, vegetable, mineral that are discrete. There's no halfway between animal and vegetable. Animal, vegetable, and mineral is an example of an unordered categorical variable, as contrasted with ordered categorical variables. If you're familiar with a Likert scale, for example, Or the scale that we're currently working with, political alignment, is ordered and categorical, which is a little bit of a funny kind of data to work with. They are represented using integers, and we just computed the mean and standard deviation of those integers. So in effect, we're taking this thing that's actually categorical and treating it as if it is a continuous numerical quantity. You can sometimes do that. It's reasonable, but you need to be cautious. One is we're assuming that these values fall meaningfully on a spectrum, which in this case is probably true, but also that the quantities are equally spaced on that spectrum. In other words, the distance from 1 to 2 is the same as from 2 to 3, and so on. Now, with things like this that are categorical, like extremely liberal and slightly liberal, what are the distances between those? We can't say that they're precisely equally spaced on a numerical scale, but at least as an approximation, taking the mean is a nice way to just explore the data. This is going to be useful because we're going to use it in a minute with this group by function. So I want to make a time series that shows how things have changed over time. So I'm going to group the data by year. So the group by function is a method. I invoke it on the data set and pass as a parameter the variable that I want to group by. What I get back is a data frame group by object that represents the result of the computation. You can think of it as a mapping or a dictionary from the name of the group to a data frame that contains that subset. So in this case, the name of the group will be the year, and the data set will contain all of the respondents for that year. One of the things that you can do with a group by object is put it into a loop. So if you loop through it, it returns a sequence of pairs where each pair is a name and a group. The name, again, is the year, and the group behaves like a data frame. So in this loop, I'm just going through and printing the number of respondents during each year. And we can see in the GSS, in the early years, they would interview around 1,500 people per year. So you can loop through a group by object, but often you don't have to because it provides a lot of the same capabilities as a data frame, including things like selecting a column. So GSS by year, that's my group by object, and I'm going to use the bracket operator to select a column. What I get back, poll views by year, is also a group by object, but it is a series group by object, and it supports operations like mean. So if I invoke the mean function on it, it will implicitly loop through each year and compute the mean of the responses to poll views. And the result of that is a series, which I can now plot. And here's what that looks like. So again, the responses were on a scale from 1 to 7, liberal to conservative. So higher values are more conservative. And it looks like there was some increase, especially in the early part of the survey. And then maybe since around 1990, it looks like it might have leveled off. The figure on the left shows the raw data just connected by lines. The figure on the right shows a local regression line. So I've taken the raw data and plotted it as the little circles. And the local regression line is computed by LOWS, which stands for locally weighted scatter plot smoothing. And it's basically just a smooth curve that goes roughly through the data. We don't have to get into a lot of detail about how it's computed. The way I computed it was by calling a function provided by stats models. The function is called LOWS, and I wrote a wrapper for it that's called makeLOWS that works with a pandas series. So most of the code here is just unpacking the series to get the values and the quantities, the x's and y's, and then compute the smoothed curve, and then put it back into a series. One of the nice things about local regression is that I'm not making any assumptions about a particular functional form. So I'm not fitting a line to the data or an exponential curve or a parabola or anything like that. It's really just computing the average of a little window of data at a time. The nice thing about it is that if there are trends in the data set, they become nicely visible in the low S curve. One drawback is that it has a parameter. You kind of have to decide how smooth you think the data is. In this example, I'm using the default value. The other danger of local regression is that it's easy to overinterpret the result and think that it is much more precise than it is. So in this example, it looks like the line goes up and then levels off and then goes down. And it looks like there are clear inflection points in, let's say, 1988 and 1999. And then since 2000, it has been decreasing, and we could compute the slope of that line, and we might say that it's 0.0135 percentage points per year. I think all of those would be more precise than we really know. If we ask these questions or report those results, we're overinterpreting this. And one way to see that is to take away the line and see if we still believe the interpretation. So here's the same figure without the line. And now it is clear that there's nothing special that happened in 1988 or 1999. And on the right-hand side of this curve, we can certainly estimate a slope, but it will not be nearly as precise as 0.0135. Here are the results with standard deviation. Again, on the left is just the raw data as a line plot. On the right, I've plotted the data themselves as circles and a low S curve that shows the trend. And one thing that's clear in either plot is that standard deviation has been increasing, probably over the duration of the survey. And again, that means that people are moving somewhat from the middle out toward the extremes. Although the difference is from about 0.133 to about 1.45. So it may not be a very big difference in practice. Which is a reminder that we are losing some information. When we compute a summary statistic like the mean, we're losing information about exactly what's happening. And an alternative is to look at the entire distribution for each year. And again, by a distribution, what I mean is how many times each response occurs. And here's one way to compute that, which is a cross tabulation. So I'm going to use the pandas function crosstab, and I'm going to pass as parameters the two series. Year is going to go down the rows of the result, and poll views is going to go across the columns of the result. So you can see the year, 1974, 1975, the responses 1 through 7, and at the intersection, that's the number of people who gave each response. So for example, in 1974, there were 31 people who gave the response 1, meaning extremely liberal. Now that result by itself tells us how many times each response occurs, but remember that there are a different number of respondents during each year. So if I compare the numbers from year to year, like going down the right-hand column, 30, 45, 34, 42, etc., those numbers are all based on a different denominator, the number of people who were surveyed. So because the number of respondents varies from year to year, a time series based on this cross tabulation doesn't mean very much. But we can throw in another keyword argument, which is the normalize argument. And if we normalize along the index, what that means is that each row will be normalized so that it adds up to 1. In other words, each row will be the fraction of respondents rather than the number of respondents who gave each response. In this example, we can see that in 1974, the fraction of people who said 7 is 0.021201. So each row represents the distribution of responses for 1 year, And each column then makes a time series that shows how those fractions are varying over time, which I now want to plot. Now I could just take that data frame and plot it, and Pandas provides a pretty good plotting function by default. But in this case, I want to customize it a little bit. So I wrote a function that allows me to plot the columns in whatever order I like and to provide a specific set of color codes. And in this case, I used Seaborn, which is the SNS library, to provide a color palette so that I can give each line a color code that means something. In this case, blue is the conventional color for liberal, red for conservative, and I'm using purple in the middle for moderate. So here's what that looks like. The nice thing about this color code is that it's meaningful. If you're familiar with this standard encoding, it's a little bit easier to interpret. One drawback I've been informed is that this particular palette is not colorblind friendly, so I might redesign this figure. But one thing we can see is that the purple line at the top is by far the most common response, and again, that's moderate. The darkest red and blue are all the way at the bottom, so it looks like there are a relatively small number of people who identify themselves as extreme. And then the middle lines, the light blue and light red, are for the other responses. Probably the thing that jumps out in this figure is that it's not changing very much. These proportions have been nearly constant over the length of the survey. One thing that is happening, as I mentioned, is that the number of people who describe themselves as extreme has increased. And we can see that a little bit more clearly if we zoom in and just plot those two lines. At the beginning of the survey, there were only about 2.5% of the population would describe themselves in either of the two extreme categories. And that has roughly doubled over the course of the survey. So it's more people, although still a small minority of the population. One of the things I want to think about as we explore data is to identify what's the story, what's going on here, and how can we communicate it? Start to think about taking these preliminary results from the data and starting to articulate them. The exercise in the notebook gives you a chance to do the same thing with party ID that we just did with ideology, and see, first of all, how those distributions are changing over time. Does the number of Democrats or Republicans increase or decrease? And whether we can see any connections between those changes and things that were happening in the world. So that's it for Notebook 2. I'm going to give you a chance to work on Notebook 3, and then we'll come back and debrief. Here's the link for Notebook 3. It covers a little bit more of the group by function and also a pivot table, and comes back to a topic from Notebook 1, which is resampling. So you can follow that link to the notebook, and in the next video, we'll debrief.